In this question, we want to work out which of these expressions will always be a square, no matter which positive integer we substitute for n. So let's start off by substituting n equals 1 and see if we can rule out some options. So substituting n equals 1, we can see that only these last two options get us square numbers, and these first three get us 2, 3, and 7, which are not squares. So we can rule out the first three options. So now that we've used n equals 1 to rule out three of our options, we can substitute n equals 2 to see if we can rule out one of the other two options. 121 is a square number, but 721 is between 26 squared, which is 676, and 27 squared, which is 729. So 721 isn't a square, and this may take you a little while to work out in a competition, but that does mean we can rule out the last option as well. However, some people may be interested in how we know that this is always going to be a square, no matter which value of n we substitute. The reason why this will always be a square is because we can actually rewrite this as the square of another polynomial, and I'm going to show you how to do that now. So we have these four terms here. Let's reorder them a little bit. So we now have these two factors and we're adding 1. So let's expand the brackets inside these square brackets. This is equal to n squared plus 3n plus 2 multiplied by n squared plus 3n, and then add on a 1. We can see that these two things differ by 2, and we can actually rewrite this as follows. So now we have n squared plus 3n plus 1 multiplied by n squared plus 3n plus 1 minus 1. Now you may recognize this as a factorized difference of two squares. So when we multiply these together, we can actually write this as n squared plus 3n plus 1 squared minus 1 squared, and then add on the 1. However, 1 squared equals 1, so these last two terms cancel, and we know that this is always a square.